Greetings, Mr. Sutton here with the Pre-Cal Honors 3-6 Part 2 homework solutions on features of rational functions. For this problem, we're trying to figure out all the intercepts, asymptotes, and holes for this rational function. So normally I would factor the numerator, but it's not really super necessary because I can see pretty quickly I'm not going to be able to reduce this at all, even if I do factor it. So we're just going to move straight ahead with analyzing everything. Let's start with the x-intercepts. So I can find those by figuring out what zeroes out the numerator of this fraction. And since nothing's going to cancel, I'm not worried about anything zeroing out both the numerator and the denominator. Otherwise, it would have been a common factor that I could have canceled. So setting my numerator, negative 2x plus 6, equal to 0, if I subtract 6 and then divide by negative 2, I've got 3 for the x-intercept. Moving on to the y-intercept, that's what I'm going to get when I plug 0 in for x in this function. So if I do that, I see that all that's left after things are zeroed out is the 6 in the numerator and a negative 4 in the denominator. So that reduces to negative 3/2. Moving on to the vertical asymptotes, those are going to be things that zero out the denominator of the simplified fraction, which is just the original fraction in this case. So if I set x minus 4 equal to 0 and solve that, I get x equals 4 as my vertical asymptote for this graph. For horizontal asymptotes, well, actually, let's think about holes because they asked about that. Nothing got canceled out, so there's not going to be any holes on this. For horizontal asymptotes, I see that I have the same degree for both my numerator and denominator, both linear, both first power. So then I take the ratio of the coefficients of that highest term. So we've got y equals, since we have the same degree, we're going to have y equals negative 2 over this invisible 1 down here next to the x, which I can reduce to just negative 2. For this one, I'm trying to get intercepts, asymptotes, and holes for this rational function. I can factor the numerator, but there's nothing that's going to cancel out with the denominator. So let me just go ahead and start analyzing the intercepts, asymptotes, and all the rest of it here. So for x-intercepts, I need to set my numerator equal to 0 and solve it to see what zeroes out the fraction. If I do that, I quickly see that I can add 1 and square root both sides, giving me x equals plus or minus 1 for my x-intercepts. For y-intercepts, if I plug 0 in for x in the original function, that'll tell me my y-intercepts. So 0 squared minus 1 over negative 3 times 0. This ends up being negative 1 over 0, which is undefined. So that means that there are no y-intercepts, because if there were, they would need to exist. For vertical asymptotes, those are going to be x values that zero out the denominator. So negative 3x equals 0 is kind of our starting point. And we see that if we divide by negative 3, x equals 0 is our vertical asymptote. For holes, there's not going to be any because nothing actually got canceled out to give us a hole. For horizontal asymptotes, this is a top-heavy function. The degree upstairs is higher than the linear degree in the denominator. So there's no horizontal asymptote because this is top-heavy. However, there is a slant asymptote if we divide the numerator by the denominator. Now to do this, we don't actually need to use synthetic division. Since this is just a single term, we can divide everything in the numerator by this negative 3x. So we can do x squared over negative 3x. And then we have a minus 1 over negative 3x, so that's plus 1 over 3x. And then I have to simplify this. Now this negative x squared over 3x can reduce to negative 1 over 3x. The x's cancel, and this is like a negative 1/3. 1 over 3x we can just ignore because slant asymptotes, that's caused as you move to the far right or the far left, as x gets really big. And as x is getting really big, this second term here is basically just reducing to 0, so we can ignore it. So negative 1/3 x is our whole slant asymptote there. Before I find all the intercepts, asymptotes, and holes for this function, it's looking like that denominator can be factored a bit, and I might be able to reduce this and cancel out some common factors. I'm not really sure, but it's worth trying. So for the denominator, right away, since I have a negative x squared, I'm going to factor a negative 1 out of everything. Otherwise, I'm not going to really know which way is up or down trying to factor this thing. So taking a negative 1 out, in a parentheses, I'll have x squared plus 3x minus 4. So that was my only change there. But now let me think here. Numbers that multiply to -4 and add up to +3. So if I had -1 and +4, x minus 1, x plus 4, that would do the job. And I see, lo and behold, I actually do have these x minus 1s that I can cancel out. So my final reduced function is going to be 1 over -1 times x plus 4. So that's going to be a little bit easier to work with, and it's also going to reveal some features of this graph that I otherwise would have missed if I hadn't tried factoring. So let's go to finding the x-intercepts now. For that, I set the numerator equal to 0. The problem, though, is that I have a constant now in the reduced numerator here. 1 equals 0 is what I would write, except that 1 never equals 0 because they're both constants that aren't the same. So there's actually no x-intercept is what this means. For the y-intercept, I plug 0 in for the x's in the original function back here, f of x. So if I plug in zeros for all of those x's, I notice that the only thing left in the numerator is a -1, and everything in the denominator is zeroed out except for 4. So -1/4 is my y-intercept then. Moving on to vertical asymptotes, these are x values that zero out the simplified denominator. So that's just this -1 x plus 4 that I have to make equal 0. And if I do that, I find that I can zero out this x plus 4 by having x equals -4. So that's going to be my vertical asymptote. For wholes, these are going to be things, x values that zero out any factors that I got canceled out. X values that would have made the original undefined but don't make the simplified version undefined. So the x minus 1 got canceled. If I set x minus 1 equal to 0 and solve that, I get x equals +1 as the x value of a whole for this graph. Finally, for horizontal asymptotes, taking a look at the original, I see that we have a bottom-heavy function. The degree in the denominator, 2, is higher than the degree in the numerator, which is just 1, just linear. Since I'm bottom-heavy, I automatically have a horizontal asymptote of y equals 0. For analyzing this graph for intercepts, asymptotes, and wholes, normally I would first try to factor and cancel things, but this one is already as simplified as it's going to get. I could factor a little in the denominator, but it wouldn't get me too much here. So let me go ahead to analyzing everything. X-intercepts, those are going to be what I get when I set the numerator equal to 0 and solve it, but the numerator is just 1. I mean, I could write I could write 1 equals 0, but that's not even true. 1 does not equal 0. So since there's no variables in the numerator that could make the numerator 0, the numerator can't be 0. That means I can't zero out the fraction, and there are no x-intercepts. All right, so for y-intercepts, we want to make x equal to 0 and plug that into the original. So 1 over 4 times 0 plus 12. This first term here just zeroes out, so this just gives me 1 over 12. So that's my y-intercept. Next, for the vertical asymptotes, those are going to be x values that zero out the denominator. So if I set 4x plus 12 equal to 0 and solve that, subtracting 12 and dividing by 4 gives me x equals -3 for a vertical asymptote. For wholes, since there's no common factors that got canceled out, there can't be any wholes for this graph. For horizontal asymptotes, this is a bottom-heavy function. The denominator is linear. The numerator is constant. So we're bottom-heavy, which means we automatically have a horizontal asymptote of y equals 0. Before we really try to analyze this rational function for all of its features that they want, it's a good idea to try factoring this. I don't know for sure that anything's going to cancel, but that numerator looks like I could definitely factor it, so it's worth a shot. If nothing else, it'll save me a little time when I actually go ahead to try zeroing things out. So I need numbers that multiply to the -12 here and add up to this 1 coefficient for the x term. That would be -3 and +4. So x minus 3, x plus 4. Much as I would like to, I'm not able to cancel out these x3 sort of parentheses here. They're not quite the same. So this is as good as it's going to get for simplifying. Let me go ahead now and start analyzing things. For x-intercepts, I set the numerator equal to 0 and solve for x. In this case, it's already factored, so I don't really have to do too much work. I just have to zero out each of these parentheses, and I see that x equals 3 and negative 4 will zero this numerator out. And I'm not really worried about any of those zeroing out the denominator because I already checked for common factors. So these are the x-intercepts. We get to move on. For y-intercepts, I'm going to try plugging in 0 for x in the original function here. So we've got 0 squared plus 0 minus 12 over 0 plus 3. All that's left when I do that is negative 12 over 3, which I can reduce to negative 4. So there's my y-intercept. For vertical asymptotes, I have to zero out the denominator. So we have x plus 3 equals 0, which means that x equals negative 3 is our vertical asymptote. Since nothing got canceled out, there's not going to be any holes. For horizontal asymptotes, I notice that I have a top-heavy function. We have an x squared versus an x to the first power between the top and the bottom there. So there's no horizontal asymptote, but there is a slant asymptote that I need to find. To do that, I have to divide the numerator by the denominator. Now I see when I'm about to do this that my denominator is a binomial. It's not just x. So I can't just go through and divide everything by x. I have to use synthetic division here. So let me get the coefficients of my numerator, which are 1, 1, and negative 12. And for my box number now, I'm going to use whatever zeroes out the denominator, the thing I'm dividing by, which in this case is x equals negative 3. It's the opposite of what I'm doing to x there. So now bringing down that first 1 times negative 3 gives me negative 3, plus 1 is going to be negative 2, times negative 3 gives me 6, plus negative 12 gives me negative 6. All I really care about is the quotient here. The remainder doesn't really do anything for me for the slant asymptote. Because, I mean, as the slant asymptote is what happens as x gets really big or really small. So this negative 6 over x plus 3, which is basically what's going on out there, is not going to affect anything. But what will affect things is the quotient here. So we're going to have y equals 1x minus 2. Before I dive in and try to find all the different features of this rational function, this is looking like something that it might be helpful to factor. I might even get lucky and be able to cancel out some common factors. Let's give it a try. For the numerator, I see that I have a common factor of x in each of these terms that I can yank out of there. That'll leave me with x plus 2 in a parentheses. For the denominator, these all have a common factor of 4 that I can take out. So if I take out a 4, I've got an x squared plus 5x plus 6. And taking another look at the denominator, I think I can factor that a little bit more. So numbers that multiply to 6 and add up to 5, those would be 2 and 3. So I can have x plus 2 and x plus 3 down there, along with the 4 that I already took out. So if I cancel out these x plus 2's then, that leaves me with x over 4 parentheses x plus 3. So this is going to be what I'm going to be using for some parts of this problem here. So it's a good thing I actually did that. So for x-intercepts now, we are using the simplified numerator and setting that equal to 0 to zero out the whole fraction. So I'm going to write x, my numerator, equals 0. And when I do that, I immediately see that x equals 0. So that is the x-intercept, x equals 0. For the y-intercept, there's two ways I could do this on this particular problem. Since my x-intercept is 0, that means I have my graph crossing through the origin. The origin also has a y value of 0. So 0 would also be the y-intercept for this graph. But if you didn't catch that, you can still plug in 0 for all the x's in the original function. And if you do that, you will see that we have 0 in the numerator, something that is not 0 in the denominator. So 0 over not 0 is just going to be 0. But again, you might have seen that already if you noticed that the origin was our x-intercept. Moving on to the vertical asymptote, these are x values that zero out the simplified denominator. There's that simplified part of this again that's so important. So we set 4 parentheses x plus 3 equal to 0. And I see when I do this that x equals negative 3 is going to zero that whole thing out. So that is my vertical asymptote. Now for the whole, these are going to be x values that zero out the original function but not the simplified function. So basically this canceled factor is where I look for the whole. So I set x plus 2 equal to 0. and I see that x equals -2 is the x value for a whole. Finally, for the horizontal asymptote, looking at my original function, I notice that I have the same degree in the numerator and denominator. These are both x squared as the highest exponent. So in that case, I take the coefficient of the ratio of the coefficients of those x squareds, which is an invisible 1 over a 4. So 1/4 then is our horizontal asymptote.